Along with technical development, human knowledge has digged down into more versatile, wider, or smaller range of technology. With this trend, material science field has traveled through meter, millimeter, micrometer, and now many interesting research is available in nanometer or angstrom level. But what's the cool thing about this tiny word? Since an atom is about angstrom scale, 1 nanometer length contains not that many of atoms, which means we can actually count the number of atoms and analyze the tiny force and effects from each atom. In this level, this energy is not continuous. We call it quantized. So this is not just small word, but we can actually find interesting phenomena such as quantum confinement or proximity effect. And my research is about building structures with various nanomaterials and seeing how they affect each other in electronics wise. Now let's think about metamaterials. In metamaterials, the properties are defined by their structure rather than the elements in it. That means you can add another cool characteristics or overcome certain deficiency we had in nanomaterials just by changing their structures. For example, a semiconductor device normally includes metal electrodes, most in cases noble metals such as gold. In photonics field, these kinds of noble metals can make negative permittivities below the plasma frequency, and it's really useful for constructing sub-wavelength resonant structures. However, in electrical way on the other hand, they barely can be tuned by external electric fields. Then how can you make this gold electrode somewhat useful? Of course with metamaterials. Now here's vanadium dioxide. It's an insulator below certain temperature, but above the temperature it becomes half-filled metal. There can be current or field effect induced phase transition in it, but it's extremely localized and not easy enough to actually detect this transition. But if we put this vanadium oxide film into an optical metamaterial absorber, this vanadium oxide acts as part of a resonating structure. Furthermore, the high thermal conductivity of gold makes Joule heat conduction into the vanadium oxide film and thermally induced transition from insulator to metal. It means you can electrically control the optical property of the materials. In this image, the metamaterial on the background of the letters show lower reflectance at zero current, but almost same reflectance at 2 ampere, and even higher reflectance at 2.2 ampere, compared to the area without patterned gold structure on it. This kind of approach can open another door to nanomaterials which have fascinating characteristics but could not present those characteristics due to certain deficiencies. It will bring us one step closer to further unknown science world, discover more things, and make our life better. Thank you for watching.